So geometry, start of week 2 of coronavirus instruction online. Today we're going to do 12-3, which is entitled Inscribed Angles on page 780, if you want to follow along in your textbook. Okay. Now I'd like you to start with just drawing a circle and having 3 vertices, A, B, and C, and then just connect A and B, connect B and C so we have an angle in there. As always with a lot of these geometry sections, the heading gives us something to focus on. So first let's talk about what is an inscribed angle. So an inscribed angle has its vertex on the edge of the circle and it intercepts and an arc. Okay. So that unpacks, we got some vocabulary just in its own definition that we can build upon. First, vertex. Remember, vertex is just where the angle is formed. So here my vertex would be B, that's where my angle would be. And then of course it intercepts an arc. Clearly it intercepts this arc right along here, arc AC. Remember it's an arc, so we gotta do a loop-de-loop, just like a rainbow. Okay. So that interesting theory actually leads right into our first theorem. What's the number? 12-11. It's called the intercepted arc theorem. It's called the inscribed angles theorem, isn't it? Inscribed angle theorem. My fault. Inscribed angles theorem. It says that the inscribed angles measure is half of the intercepted arcs measured. So in this very specific example, what that means is the measurement of angle B is equal to half the measure of arc AC. So without not getting into it, let's do an example. So, of course, I need a new circle. Again, my ultimate frisbee will make just do. Example 1. Inscribed angles. Let's see. I want something like that. Of course, I'm going to need to label my vertices. Well, P, Q, R, S are good enough. Oh, I need one more for T. What if I told you that ST was 30 degrees? That this right here, angle Q, was 60 degrees, and we were trying to find A and B. Okay. So, A should be the easier one to solve for right away because I get an intercepted arc directly from my inscribed angle. So, angle Q, or measure of angle Q, has to equal 1/2 measurement of arc PT, because again, that's my inscribed angle, and its intercepted arc would be that. As this is my angle, so my arc is between those two endpoints. So, if Q is 60 degrees, and I get 1/2 of A, how can I get A by itself? Well, I'd have to undo my 1/2, which would be by multiplying by the reciprocal. 1/2 times 2 is 1, so multiplying by 2 to each side. A has to be 120. Now, if we were to look at solving for B, again, measurement of angle R has to equal 1/2 of the measurement of the arc PTS. And as we see PTS, well, this part's 30, and this part is A. I would get 30 plus A, but since I already know A, I get 30 plus 120. So I get 1/2 of 30 plus 120 equals measurement of angle R. Well, 30 plus 120, well, that's 150. And then I just need to find 1/2 of 150. So measurement of angle R, or in this case, B, equals 1/2 of 150, which would be 75. So my answers would be A is 120, and B in this case is 75. Okay. In this specific case, we had to do A first. Because if I started with B, I would have gotten this weird situation with algebra where I would have gotten 1/2 parentheses 30 plus A. And it got me stuck, so I needed to find A first. If you try to find B first, you would realize that as well. Now the interesting thing is, with this theorem, is we actually get 3 different corollaries. So you're going to need to draw 3 circles here. So we get 3 corollaries. Remember, corollaries just means it's closely related to a theorem, but it's not different enough to warrant its own proof. So you need 3 circles. Corollary 1. Two inscribed angles that intercept the same arc are congruent. So, if I get an arc like this, and let's say this, they both intercept this arc right here. like this blue one would intercept this arc right along here, and my red one would intercept, again, that same arc because it shares the same endpoints. So, what this means is, since they share the same endpoints, let's say, for example, it was, I don't know, 120. Okay. Remember, because our our inscribed angle would be half of that, they'd both be half of 120 or 60, and 60 is always going to be congruent with each other. So that's why these two would be congruent, because they intercept the exact same arc. Again, I don't know it's 120, I just use that as an example. Okay. Corollary 2 says that intercepted arc, if the intercepted arc is a semicircle, the inscribed angle is a right angle. So let's say I have a center of a circle and I have my diameter. So if I have an angle and it intercepts that entire arc, well, that entire arc, if it's cut by diameter, would naturally be 180, and if this angle has to be half of 180, it has to be a right angle. That's all it's saying is if the intercepted arc is a semicircle, which in this case it is, then the inscribed angle would be a right angle. And the last one, opposite angles of inscribed quadrilaterals are supplementary. Okay, a lot to unpack there. First, we talked about inscribed angles. We haven't really talked about inscribed figures. Now, inscribed angles are, again, angles formed inside the circle that rest on the edge. So, an inscribed quadrilateral follows the same rules. Quadrilateral being 4 sides, so we have 4 sides that are all within the figure. Okay, boom. 1, 2, 3, 4 sides, so I know it works. So now we need to talk about this idea that they are supplementary. Your opposite ones are supplementary. Well, let's look at it this way. If I were to just look at, just look at angle 1 and angle 2. Well, angle 1 would intercept this part to this part, and angle 2 would intercept, if I'm following angle 1, follows this part and to this part. So I would intercept this arc. Now, if I'm looking from angle 2's perspective, I get to here. I'll use a different color. If I were to look at it from angle 2's perspective, I'd get from here to, well, here. So I would intercept this whole thing. So together, they form 360 degrees. So if 360 degrees divided by 2 is 180, then the interior angles have to add up to be 180 degrees, which is the exact thing that supplementary means. So all it says is that opposite angles have to add up to 180 degrees. If we were to add finite value, say that this one was, I don't know, 89 degrees, this one would be like 91 degrees. It'd have to be something like that. On to example 2. This one will do 2 of them with it, so you need 2 circles. I call it use corollaries. I think I'm getting better at tracing my frisbee. Alright, let's see, I need some figures. So let's see, first. Let's make this y, and this is 70. That'll be good enough for that one. And how about the other one? Let's see, we have So I'll read these out here just in case you can't quite see them. I have 70 degrees for this arc. We'll make it way bigger. I drew it wrong. Let's go. That seems pretty close to 110 degrees. I have y right here. This is a 40. Then of course I have a 60 degrees for this arc. I have a 70 degrees for this arc. I have an x. I have a line through the center, and then I have a y, and then I have another line. Okay. So, let's start with the 40, or I'm sorry, with this one right here. Now my 40 is this angle right here, and it clearly intercepts, it edges right here to here. So, using my idea of if the angle is 40 degrees, it has to, the arc is 1/2, or half of that is the arc. I can multiply by 2 to each side, so the arc has to be 80 degrees. Well, which is good because, again, off my corollary, my y value intercepts the exact same arc, so it would be half of 80, or 40, which goes to show that my corollary was true, that those are the exact same value because they intercept the exact same arc. On this one, I'll tell you what, let's have some fun. Let's find this one as well. I made that one a z. Okay. So first, well, y is really easy. Y is right here to here, and the arc is 70, so half of 70 equals y, so y has to be 35 degrees. Okay. Here we have x, and x is very interesting because its intercepts are a semicircle because my diameter goes through the center, so it has to be 90 degrees. Because it intercepts semicircle. And last but not least is my z. Now here's my question is, what shape is formed there? Well, naturally that's a triangle. And just because a triangle's in a circle, is it going to change the total number of degrees the triangle has? Nope. So triangles always have 180 degrees. So 180 equals x plus y plus z, but I already know that my y is 35 and my x is 90, so I get 90 plus 35 plus z, so I get 90 plus 135, which is 125 plus z equals 180. I can subtract 125 from each side, so my z has to equal 55 degrees, or 55 is fine. On to the next one, theorem. This one doesn't have a specific name, unfortunately, but we need a circle for it. And of course, we need some drawings. Let's see, B, D, C, A. Okay, so theorem 12-12 starts with something like this. And it's very interesting because it reads out like this. Measure of an inscribed angle formed with a tangent line is 1/2 the intercepted arc. So what that means is, in this very specific example, the measurement of angle ACB, ACB, so this angle right here that we're talking about, equals, again, 1/2 of the arc that it intercepts. So arc B, or CDB, this arc right here. Now, know what you're saying, I'm sorry, what you're probably thinking is, that sounds an awful lot like the first one. It essentially and functionally is. I guess the only nitpick you can make is this is probably not technically an inscribed angle, just because an inscribed angle usually has both of its edges, or I'm sorry, both line segments that would intercept the circle somewhere. But the function is the same. Technically, you could probably call this, instead of an inscribed angle, a chord and a tangent line. So a chord would be BC, as we talked about in our previous section, and then tangent line AC. But the functionality is the same. And then, of course, let's do an example with it. And we're going to call it use angle measures. So, like all of our examples, again, we need a circle. Now this one we need a chord. Let's call it PQ. We are going to need a line that is tangent to the circle at Q. So let's call it line SR. And I will tell you that we need another point out here, let's call it M. I will tell you that the arc, PMQ, the measure of that arc is 212. And we are going to find the measurement of angle PQR. So I'll give you a quick second there to jot that down and catch up. Okay, so there's two ways we can go about finding this. We'll cover both of them here. The first one, they both start the same way. We would label that this is 212 degrees. Okay. So method one would be to say that this angle right here has to be half of that 212. So angle SQP equals 1/2 of that 212. So angle SQP has to be half of 212, so 106. And then we have to say that angle SQP and QPR as a total form a line. So in total they have to be supplementary, so 180 degrees. So angle SQP plus angle PQR equals 180. And because we know SQP is 106, 106 plus PQR equals 180. And then we could just subtract 106 from each side. So angle PQR equals 74 degrees. Okay. That's one way we could have done it. We could have said 212, boom, supplementary lines. Okay. The other way we could have said it is we could have said that because PMQ is 212 degrees, well, what left of the circle is there? If circles are 360 degrees, but I know that that's 212, it has to be left for whatever is left of arc PQ. So I can subtract 212 from both sides. So that would give me, let's see, 148. And then I would know that measurement of angle PQR would have to be half that 148, because again, PQR intercepts that as its arc. PQR is right here, its arc it intercepts would be that purple value we just found. So I get half of 148, which would be 74 degrees. So that would be the second way you could have gone about solving it. Could have said that this was 212, so the rest has to be 148, and find that value. Okay. That's actually all I have for notes. This one felt pretty quick going through. I don't know. Time is an illusion. I'll find out later when I upload this. Thank you for everyone who is motivated enough to help make this work. I appreciate your effort, and I hope you guys have a wonderful week. Thank you.